What's up, everybody? This is Aircrete Harry, and today I'm doing a thermal battery test. So what you see here are numerous samples of different materials that I will be starting a fire in the center of this pit and allowing them to absorb the heat and test how long they can retain that heat and which of these materials is a better insulator and better for retaining the heat for a thermal battery. Now, recently I had a workshop in Darwin. Mr. Honeydew Carpenter attended, and he brought his rocket mass stove heater, and he fired it up for the first time on the property here, and it was pretty cool because he had a fire burning for about 1 hour at the nighttime, and when morning time came, we touched the rocket mass stove heater, and it still felt warm to the touch. Now this was right here. He was right about there in this spot. So it was outside all night, and it was about 54 degrees at night with the wind blowing, and it was pretty cool because it still had heat. Had that rocket mass heater been inside of a house with no wind blowing, it would have been pumping heat out all night. So it's pretty cool. It confirms to me that, well, it showed me that the Aircrete is also a thermal battery. Now, I tested Aircrete with a blowtorch before, and it was a great insulator, and I didn't really think it would work as a thermal battery at all, because I had people ask me about using Aircrete for a radiant floor heating system, and my thought was it was just going to insulate and not allow that heat to come up. So based on what I saw with the rocket mass stove heater that had Aircrete in it, it seems like it does work as a thermal battery. Now, I have a rocket mass stove heater design that I was building, and I was going to be using Aircrete for the insulation, and it looks like that sucker might just be pumping heat out. Now, I have a slightly different design than the one that was tested here on the property. So anyway, this test here is going to be to see how these different materials work. So I have a thermal imaging camera. This is the Flare C3, and I'm going to be taking images. I'll be putting the images in the video. This has too much glare to show you on here, but I've already taken some images of the, get focused here again, of the weight. There's a 5-pound weight, steel weight that's right there. There's a rock, one of these shelf rocks, that's right there. I have this bar here is a piece of aluminum. It's about a 1/4 inch thick piece of aluminum. This rock here, this sample, is sand and cement only. So I have 2 samples here of a sand cement mix to see how that compares. I have 2 samples of E.P.I.C mix, and these are 2 slightly different mixes here. And then the rest of the rocks you're seeing around were one large Aircrete brick that I had that I broke up. And so I have a bunch of pieces of Aircrete all the way around. So what I'm about to do now is get a fire going. I have a bunch of wood over here. I'm going to put all that wood in the middle and just get it going. So I'm going to pause this while I fill this up with wood. Okay, so I have my firewood here in the center. You can see my steel plate there, and these are Aircrete samples. This is an E.P.I.C mix, so is that one. This is a regular rock, one of these rocks here. I have in there is the piece of aluminum bar. This is the sand cement mix, those two. So I'm going to get this fire going. I'll let it roar. I'll take thermal imaging samples every every 10 minutes or so. I'll do a thermal imaging all the way around, and we'll see how well the Aircrete or the E.P.I.C or the regular cement or the aluminum bar or the piece of metal plate or the rock we'll see how well each of them works as a thermal barrier. As a thermal battery. So I'm gonna get this fire started, and I'm gonna pause after I get it started and come back occasionally so you can see how it's going. Yeah, this might have been a little cooler to do at night, but as soon as I had the idea, I said, let me get it going. I love doing these type of fires at night. It just gives you such a nice mood, especially when you have like the stars are out and the mountains out, or the mountain hills out, and the stars are out. It just looks so cool. So let me just take an image now and see how this is heating up already. So I'm getting, and I'm pretty sure this flare camera has a max that might be, well, I don't know, I'm gonna have to look it up. It's probably under 400 degrees. So I'm just gonna take an image. Let's see if we can. I got all glare on my camera here. Okay, so you can see the temperatures increasing. Take a picture. All right, so I'm gonna walk around, just see how the blocks are faring. Okay, so I've had these pieces burning, I guess it's been at least an hour or so, and the fire is still going. So I actually touched the back of the Aircrete samples and they feel cool to the touch. So what I'm going to do is take all the samples, put them in the bucket, and transport them to the shed over there so that I can, in the shade, see, and without wind blowing on them, see how long they retain the heat. And I'll take better images, thermal images, once I get it inside the shed there. Okay, so we've put all of these in the fire pit, and we had a fire going for about an hour. Now we're going to look at them with the thermal imaging camera. So let's see if I can focus this. Okay, so here is the metal plate, the metal weight, and you can see that puppy is glowing, and that's reading 300. It's reading pretty much max. 356. I think that's the max on this camera. I'm gonna take a picture of that. And we have the aluminum bar right here. That aluminum bar is already cooling down. It's reading 261, 290 I saw. Down here it's already cool. 148, 142. So I'm going to try to take a reading at its maximum. Alright, I'll take a shot there. Then these two samples here are the sand cement mix. Let's see how this is reading. I'm getting max temperature here, like 360. I think this is the back side of that sample, which is also good to see. I'm going to flip it and see if that one looks hotter on the other side. Nope. That's going to be the cooler side. It's reading 188. The other side is the side that was exposed to the fire. This side here, because that one's reading hotter. What else? Here we have our two E.P.I.C mix samples. There were two different mixes. And let's see. This side looks burnt. Yeah, I guess these were the faces exposed to the fire. And we're getting at the hottest point 166, and the other sample at the hottest point looked like 222, 227. Over here is our rock. That's just a regular rock that was on the property, and that one's still maxed out at 356. Again, I think 356 is the maximum this thermal imaging camera can go up to. Now all the other samples we see here are Aircrete, and this Aircrete sample is reading 299 at the highest. Okay, so we're in this shed for a couple of reasons. The first is so my camera doesn't shut off from overheating from being in direct sunlight. The second is so that these samples are all indoors, inside, so that the wind's not blowing on them. Kind of to replicate what would be happening in your house if you were using any of these different examples as a thermal battery. So what we're going to be looking for is the sample that we have here that holds the heat the longest. The only thing I can say about the Aircrete that's different from the experiment I'm doing here now to the example that I saw with the Rocket Man stove heater that Honeydew Carpenter made, there's two other ingredients, variables that were in the Rocket Man stove heater that's not in this. The first is the inner core of that Rocket Man stove heater is an aluminum silicate, I believe. And it's a very dense, very strong material that's the firebox of that Rocket Man heater. I don't have a sample of that. That might be a very important ingredient. For all I know, it's that ingredient that was radiating the heat for a long time. I'm not sure. I do know a furnace was made with the Aircrete, and that retained the heat. But and then the second thing that's different from the Rocket Man stove heater is it was covered in a sheet of aluminum all the way around, 360 degrees. And so those are two variables that's not in this uh, demonstration here in this experiment. So Aircrete, as I said, it's a very good insulator. Like this piece here, that's reading. This is the biggest piece that has the highest temperature reading of 259. I'm going to flip that sample over and we'll see how the backside is. I'm almost certain this is the side that was exposed to the fire. Yes, because there's no charring on that side. And the backside of that sample, look at that. 87 degrees. It's reading 87 degrees on the backside. And this is part of the insulative value that Aircrete has that I like so much. And this is also why it makes for a great fireproof structure. So I'm going to put the hotter side out, and we're going to keep looking and seeing what the difference is in the temperatures. Again, we're going to look at, this is the regular concrete. This one was in the direct fire probably for the longest. And then the sample next to it, you can see it's 213 degrees. This is the metal weight. Now I didn't quite time this. I'm gonna have to look at the video footage to get a calculation of how long it's been. But we can see here the Aircrete, it's already pretty cool. All the Aircrete samples, these were all in the fire. Some of them were in more direct heat than others. This is the rock. It's still maxed out. It's close to max on there. Now another thing I'm thinking is if these Aircrete samples were covered in a stucco, and they were allowed to heat up really good, that's maybe the variable that I don't have in this experiment, where the Aircrete is not covered in either sheet metal or in a fireproof, or rather in a highly insulative stucco. There's a ceramic bead stucco mix that I make that's super insulative. I mean, it's really just a super thermal battery. Okay, so it's been about another 20 minutes has gone by. And let's take a look at our samples through the flare camera. Again, this sample on the far right is sand and cement. It's a regular concrete mix. 4 parts sand, 1 part cement. Same for that sample. The bar is a aluminum bar, 1/4 inch thick. This is a 5-pound weight. It's a steel weight or iron, whatever it is. And then all these are Aircrete up top. This is just a rock. And these are 2 E.P.I.C samples. So we're going to look at them again on the flare. So our sand cement mix, concrete, is still reading pretty high at 240. Yeah, I'm getting about 245. Our rock here is reading 222, 235. It's one of the highest readings I saw. I got it at 232. This is our Aircrete. Aircrete is reading 166. I'm getting 166 at the highest. 168. These are the E.P.I.C samples here. That stripe, that's just the sunlight. So that's showing up on the flare camera also. That heat. Let's see what the sun is reading. The sun on the floor is reading 120 degrees. About over here. Getting 120, 130 degrees on the floor, this sunlight. So far, the sand cement mix is holding the temperature really good. The regular rock, you can see from the color, is also whole. I'm going to put the hottest pieces together and just keep an eye on those pieces. Okay, so those are the hottest pieces that are still holding heat. And we're going to let them sit a little longer and see how they're doing after about another 10 minutes. Okay, so about another 12 minutes has gone by. Let's take a look at how our sample's doing on the flare camera. So our sand cement mix at the hottest point, we're still reading about 107 degrees. Our rock is still 202 or 204. Let me separate the rock a little more. Now, obviously, there are some other variables I'm not accounting for in this test right now, and that is the different densities and thicknesses of all the materials. For example, the metal plate is about a ½ inch thick compared to the sand cement mix, the concrete, which is about 5 inches thick. So if that metal plate were 5 inches thick, it probably would be holding heat a lot longer as well. The rock is tapered. It's thicker on one end and thinner on the other. And the Aircrete sample over there is about the same thickness as this rock. And these E.P.I.C samples are the same thickness as the concrete. So I'll give you another look through the flare. So here's our rock over there. I'm getting a high of 201. This is the concrete. I'm getting 203, 204 at the hottest point. Our metal plate, it's gone down. It's reading 140. the aluminum bar. It's reading 110. I flipped one of the E.P.I.C samples over. So this sample here is the back side, and you can see on the camera how much cooler the back side is opposed to the front. The back side of that E.P.I.C sample is, it's reading 88 degrees on the back side there. This is the other E.P.I.C sample. It's reading 127 degrees. This is the other concrete sample, reading 170. So the three I'm going to keep my focus on are the concrete, the rock, and the Aircrete. This is the Aircrete in the back there, is reading 141. So one of the things that's different from this test opposed to the rocket stove is the rocket stove had sheet metal all around it, as well as aluminum type of ceramic. That's the firebox. So the Aircrete was sandwiched in that case, as well as in the case of the forge. The forge that was made, I believe, was also a sheet metal on the outside. So that metal on the exterior of the Aircrete may be part of the reason why it was able to absorb the heat and retain it for a long time. So I don't have any Aircrete, inside of any sheets. So one of the next experiments I'll do is I'll put the Aircrete sample in the oven so that there is heat all the way around it, on all sides of it, and I'll put it on broiler mode for an hour. Then I'll take it out and I'll compare that test to this test, where only one side of the block was getting heat because the other side is still cool. If I turn this block around, and I can touch this now, it's radiating heat. I wouldn't touch this one at 200. Yeah, that's super hot. That would burn me. But the Aircrete, I'm touching, and it's cool. So that's the back side of the hottest Aircrete sample. And we'll take a look at that. The back side is, oh, had it upside down there. Backside is reading 104, and the top of that block is reading 112. So I'll flip that back around. And the front is reading 138. So based on this experiment, the concrete sand cement mix that I have there is so far the best at retaining the heat. So at this point, I would say the sand cement mix is the best thermal battery out of these samples that I tested. Again, a big variable is the metal plate is not as thick as the concrete sample it's next to, but you really wouldn't want anything that thick anyway, because then it'd just be tremendously heavy. Like, holy cow, that would be heavy. And but this was just the metal that I had on hand, and I just wanted to see how long that metal would retain the heat, and it's already dissipated more than the concrete sample. And also the rock has done very well also. And so anyway, the last test I'm going to have for the Aircrete sample and even the E.P.I.C brick is I'll put them in the oven for an hour on broil mode. I'll let them absorb as much heat as they can. Then I'll take them out and do testing to see which of those two will retain the heat the longest. Anyway, that's it for now. This is Aircrete Harry. Peace out. I hope you enjoyed my thermal battery test. Hasta la vista.